Dear students, welcome to today's class. Today, we will look at number systems once more. So, as you know, when you work with the computer, all the data that you have will be represented in computer memory. In the computer memory is organized in terms of bits and bytes. Each bit can store a unit of information that is 0 or 1, and a byte comprises of 8 bits. And then we can have multiple bytes which make up a word. So every data item that is stored in a computer must be represented in terms of these bits. And therefore, in a computer, we use the binary representation. The conventional representation that we use in our normal day-to-day life is the decimal representation. And the hexadecimal representation comprises of 16 different digits, and it is a convenient way to represent binary numbers. So first, let us see, just revise what you have done in school. What is a decimal number system? In the decimal number system, you have 10 digits, 0 to 9, and you can have a number like, say, 346. Now, this number, there are 3 different digits, and each position has a different weight. So this least significant bit, or LSB, that is the rightmost bit, has a positional weight of 10 to the power 0, that is 1. The next bit to the left has a positional weight of 10 to the power 1, and the next bit has a positional weight of 10 to the power 2. So the total number is equal to, the value of the number is 3 into 10 to the power 2 plus 4 into 10 to the power 1 plus 6 into 10 to the power 0. So this is a number whose base or radix is 10. So now, just erase this. So now let's look at this number 6234. 6234 is a number to the base 10. And this number has 4 digits. So the least significant digit, 4, it has the positional weight of 10 to the power 0, that is 1. Then 3 has the positional weight of 10 to the power 1, that is 10. 2 has the positional weight of 10 squared, that is 100. And 6 has the positional weight of 10 cubed, that is 1000. And therefore, this number can be written as 6 into 10 cubed plus 2 into 10 squared plus 3 into 10 to the power 1 plus 4 into 10 to the power 0. So in general, a decimal number of n bits, the ith bit has a positional weight of 10 to the power I, and we can find the value of the number in terms of multiplying the ith digit with the positional value of the ith digit and adding up this positional value of the different digits. So now, if you have a n-digit decimal number, how many unique decimal numbers can it represent? So if you have an n-digit decimal number, each digit can have 10 values, 0 to 9, and therefore the number of unique n-digit decimal numbers are 10 to the power n. For one digit decimal number, you can represent 10 numbers from 0 to 9. If you have 2-digit decimal numbers, the first digit can be 0 to 9, the second digit can be 0 to 9, and therefore you can represent 100 different numbers. It is 10 squared different numbers. In general, if you have n digits, each of these digits can represent 10 possible digits. So the total numbers are 10 to the power n. So what is therefore the largest n-digit decimal number? If you consider only positive numbers, 0 or positive numbers, the smallest number is all n bits are 0. And the largest number is all n bits are 9. And this number is 10 to the power n minus 1. So a n-digit decimal number, unsigned number, can represent numbers from 0 to 10 to the power n minus 1. Now coming to binary number system, there are two digits 0 and 1, and each digit position has a weight which is a power of 2. So if you have a number like this, if you want to find its value, you first look at the least significant bit. Its value is 2 to the power 0, that is 1. The next bit to the left has a positional value of 2 to the power 1. Then this is 2 square. This is 2 cube. This is 2 to the power 4. 2 to the power 5. 2 to the power 6. So if you have this number 1101, which is a binary number to the base 2, the value of this number is 1 into 2 cube plus 1 into 2 square plus 0 into 2 to the power 1 plus 1 into 2 to the power 0. So in general, if you have a n-digit binary number, you can find the value of the number by multiplying each digit with 2 to the power I, and then take the sum. How many different non-negative n-bit binary numbers are there? There are 2 to the power n such numbers from 0 to 2 to the power n minus 1. And these are the enumerations of the 1-bit numbers, 2-bit numbers, 3-bit numbers. In 3-bit numbers, the smallest number is 000, and then we have all these numbers up to the largest number, which is 111, which is 2 to the power 3 minus 1. So what is the largest n-bit binary number? It is 2 to the power n minus 1. Now suppose you want to represent the number n in binary. How many bits do we require? First, we want to find out how many bits are needed to represent n different binary numbers. So if there are 1 bit, we can have 2 numbers. 2 bits, we can have 2 square numbers. We have already discussed this. 3 bits, we can have 2 cube numbers. N bits, we can have 2 to the power m bits, we can have 2 to the power n numbers. So therefore, if we want to represent a number which is n, it will require, so suppose n is equal to 2 to the power m, then the number of bits is equal to m, which is log n to the base 2, and the ceiling of that. Why ceiling? Because you require an integer number of bits. Suppose you want to have you want to represent the number n. So how many different numbers must there be? You want to represent n. Suppose n is equal to 100. So there must be at least 101 different numbers from 0 to 100. How many bits do you require? If you want to represent, if you use 5 bits, you can represent up to 0 to 31. 6 bits, you can represent 0 to 63. 7 bits, 0 to 127. Now, so we have to represent the number 100. So if we use 6 bits, we can only use 0 to 63. Therefore, we want to use 7 bits, because with 7 bits, we can represent up to 127. So we take log of n plus 1 and we take the ceiling. So log of 101 will give us 6 point something, and we take the ceiling, we get 7. Now let's look at fractional numbers. Suppose this is a number, mixed number, which has both an integer part as well as a fractional part. Now what is the value of this number? We have already seen how to find the value of this part of the number by giving the place value of each position, starting from left of the decimal point. Now, if we look at the digits which are to the right of the decimal point, their place values are the first digit to the right, its place value is 10 to the power minus 1. The second digit to the right, 10 to the power minus 2. Third digit on the right, 10 to the power minus 3. So we can obtain the value of this number as 6 into 10 cubed plus 2 into 10 squared plus 3 into 10 plus 4 plus 1 into 10 to the power minus 1 plus 2 into 10 to the power minus 2 plus 5 into 10 to the power minus 3. So in general, if we have a number like this, which has n digits to the left of the decimal point and m digits to the right of the decimal point, so we can compute the value of the number by multiplying each digit with its place value. Similarly, if we have a binary fraction, for those bits which are on the left of the binary point, the decimal point, the place values are 2 to the power 0, 2 to the power 1, 2 square, 2 cube, etc. And the place value of the digits to the, or the bits to the right of the decimal point are 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, and so on. And therefore, we can compute the value of the number by summing this up. And in general, for a binary number which has n bits to the left of the decimal point and m bits to the right of the decimal point, this red represents the value of the number, the integer part of the number, and this blue represents the value of the fractional part of the number. Next, we will look at how to convert a binary number to a decimal number and vice versa. First, let's look at a binary to decimal conversion. So we have seen that each digit position of a binary number has a weight, and therefore we can compute the decimal value of the number by multiplying every bit by its weight. So we can say we take a summation bi to the power I, and I varies from minus m to n minus 1. So minus m to minus 1 are to the right of the decimal point, and 0 to n minus 1 are to the left of the decimal point. And we can compute this to get the decimal value of a binary number. Let's work out an example. Let's take this number 101011. What is its decimal equivalent? So we find this has a place value 2 to the power 0. The next bit has a place value 2 to the power 1. This 2 squared. This has place value 2 cubed. This is 2 to the power 5. So 1 into 2 to the power 5 plus 1 into 2 cubed plus 1 into 2 to the power 1 plus 1 into 2 to the power 0, which is equal to 43. So this number is equivalent to 43 in decimal. Now let's take a fractional number, pure fraction, 0.0101. So its value can be computed as 1 into 2 to the power minus 2 plus 1 into 2 to the power minus 4. And we can have a number which has both the integer part as well as the fractional part, and we can also compute it. Next, let us look at a decimal to binary conversion. So we have given a decimal number, we want to have the binary representation. So for ease, what we will do is that we will look at the integer part of the number and the fractional part separately. So for the integer part, first we'll find the binary representation, and then for the fractional part, we'll find the binary representation, and then we'll combine them. For the integer part, how do we compute the binary representation? We take the number and we divide by 2. If we divide the number by 2, the remainder gives us the rightmost digit of the number. If I take a decimal number, divide by 2, the remainder gives us the rightmost digit of the number. And the quotient gives us the rest of the number stripped of its rightmost bit. Okay, so if you have 4, 3, 1, 5, and if you want to convert it into binary, if we divide this number by 2, what is the remainder? It is 1. Therefore, the number will have 1 in the rightmost place. And the rest of the number is, when I divide by 2, what is the quotient? The quotient is 2157. So the rest of the number is 2157. And now to get the second bit from the right, we can again divide by 2. The remainder is 1. And then we will have a quotient which is 1078. Again, we will repeat the same process. And every stage we collect the remainders, then we write the remainder in the reverse order. Or we can collect the remainders and start writing them from right to left. So this is for the integer part. For the fractional part, what we will do is that we will take the number and repeatedly multiply the given fraction by 2. And the integer part, when we multiply by 2, the integer part will be either 0 or 1. And we will accumulate this integer. If the integer part is 1, we will chop it off. And the integer parts will then be arranged in the order that it is obtained. Let's look at an example. First, let us look at a integer number 239. So we want to represent it in binary. So we have divided 239 by 2, and this is the remainder 119, and the quotient is 119, remainder is 1. We divide 119 by 2, remainder is 1, quotient is 29, and we continue doing this process until we get a value so that the quotient is 0. Now, these are the remainders that we have obtained, and we write them in the reverse order. So that this is the rightmost bit, this is the leftmost bit. And if we write it this way, 1, 1, 1, 1, then 0, 1, 1, 1, 0, 1, 1, 1. This gives us the binary representation of this number. Okay. Now, why does this work? So let us see why, if we take a binary number and keep dividing it by 2, why do I get a binary number, and why should the last remainder be the first bit? So for this, let us see. We've already seen that the decimal number is represented by the summation of the powers of 2. That is, if you are given the number 19, it is 16 plus 2 plus 1, which is 1 into 2 to the power 4 plus 0 into 2 cube plus 0 into 2 square plus 1 into 2 to the power 1 plus 1 into 2 to the power 0. And the binary representation of 19 is this binary coefficients, which is 10011. So 10011 in base 2 is same as 19 in base 10. The conversion, the whole point of conversion from decimal to binary is to find these coefficients. And how can we find these coefficients? We can repeatedly divide by 2. So when we take 19, 19 equal to 1 into 10 plus 9 into 1. How do we get the 1 and 9? You divide 19 by 10, and the quotient is 0 until the quotient is 0. So if you want to get the binary representation, we have to keep dividing by 2 and accumulating the remainders from right to left. This is one more example, 64. We keep dividing, and these are the remainders. We write the remainder in reverse order, and we get 1 and then 6 zeros. For the fractional part, as we have said, we multiply the given fraction repeatedly by 2, accumulate by integer part 0 or 1. If the integer part is 1, chop it off. and arrange the integer parts in the order they obtained. Let's look at an example. Suppose we have this fraction 0.634, we multiply by 2 and we get 1.268. So now we keep this 1 and this 1 comes as the first bit after the decimal point. But we chop this 1 off and we get 0.268. We multiply 0.268 and get 0.536. So this 0 will come here. Then we chop off the 0, we get 0.536, multiply by 2, we get 1.072. Now for this 1 will come here and we chop this off, we get 0.072, multiply by 2, we get 0.144. 0.144, this 0 comes here, multiplied by 2, we get 0.288, this 0 comes here. And we can continue to more number of bits if we want to get higher precision. But we can stop if we have limited precision. So, and these numbers, this 10100, in this order gives us the binary digits to the right of the decimal point. If we have a mixed number like 37.0625, we take this 37 and we get convert it to the integer part. Then separately we take the fractional part, convert it into binary by repeated multiplication. This we do by repeated division, and then combine them to get the representation of this mixed number. Next, we'll briefly talk about the hexadecimal number system. This is a number system to the base of 16. There are 16 digits. So we will call them 0 to 9 is the first 10 digits. And then we have the digit A, B, C, D, E, F. A represents 10 in decimal, B 11 in decimal, C 12 in decimal, D 13 in decimal, E 14 in decimal, F 15 in decimal. So there are these 16 different digits. So if we have this hexadecimal number 2A3F, so this F, the LSB, its place value is 16 to the power 0. This 3 has a place value of 16 to the power 1. A has a place value of 16 square and 2 has a place value of 16 cube. So 2A3F to the base 16. If you want to convert it into decimal, it is 2 into 16 cube plus A into 16 square plus 3 into 16 to the power 1 and F into 16 to the power 0. And you recall A is equal to decimal 10 and F is equal to decimal 50. Okay, so 2A3F16 is 2 into 16 cube plus 10 into 16 square plus 3 into 16 to 1 plus 15 into 16 to the power 0, which is equal to 10815 in decimal. Now let's look at binary to hex conversion. This is very simple. For the integer part, so as we see, a hexadecimal number can represent 16 different numbers. A binary, 16 different one digit can represent 16 different values. A binary number on the other hand can represent 2 values. So we can take group of 4 binary numbers and have one hexadecimal digit to represent it. So if you want to do binary and hex conversion, suppose we have this number. So what we will do is that we will group 4 bits. We'll start with the decimal point. We'll start with the decimal point. And then we will club together 4 bits at a time. And then, so this is the first 4 bits to the left of the decimal point. And then we have only 3 bits. So we will use a 0 to get 4 bits. Similarly, to the right of the decimal point, we take 4 bits, 0, 1, 0, 0, then 1, 0, 1, 0, then 1, 0, 0, 0. So we club these bits, and for each bit, we find the corresponding hexadecimal code. So what is 1100? It is 12, that is C. What is 0100? This is 4. So it's 4C. Dot, what is 0100? 4. Is 4C dot 4. What is 1010? It is 10. That is A. 1000 is 8. So it is 4C dot 4A8. So we will do this clubbing, and based on that we can find the hexadecimal number. So to the left we'll club, to the left of the decimal point we'll club 4 at a time until the last group we may have to pad by leading zeros. Similarly, to the right of the binary point we club 4 4, and we may have to pad by trailing zeros. So here's an example. We take this number 10111.11. So we group by 4s, and by grouping by 4s we get 0111, and then we have this one alone. So we will add 3 leading zeros to get 0001. Similarly, to the left of the decimal, right of the decimal point, we will add 2 trailing zeros to get 1100. Then for each of them, we'll find the hex code based on their place values. So 0001 is 1, and 0111 is 7, and 1100 is 12, that is C. So this number is 17.C. So similarly, you can work this out. I leave it as an exercise, and these examples are there in the slide. Please follow the procedure to work them out. How do we convert from hexadecimal to binary? We can translate every hexadecimal digit into its 4-bit binary equivalent, and we can discard the leading and trailing zeros if desired. For example, suppose we take this 3A5 is a hexadecimal number. For 3, we write 0011. This is for 3. For A, we write 1010. For 5, we write 0101. And this gives us the binary representation. If we wish, we can remove the 2 leading zeros. How do we write 12.3D? For 1, we get 0001. For 2, we get 0010. Then we put the point here. For 3, we get 0011. D is 110. Okay. So is this all right?